started. Okay. So welcome everyone to our energy storage at PNNL webinar series. As we're looking at this, we're trying to bring in experts and partners from as we look at the different topics in energy storage. And so today we are proud to have looking at flow batteries with several industry experts in there and trying to look at the future of flow battery technologies. As we look at what's out there, we're seeing a bigger push towards longer duration energy storage, and that's spurring additional interest in technologies like flow batteries that can be able to handle something beyond typical 4-hour dispatch. And so really wanted to get what the state of the art is today and answer any of your questions. So please feel free to put your questions in the chat. Our format today will be, we will allow each speaker to go through and give their presentation. We will take a couple questions for each speaker. And then at the end, we will hopefully have time to answer more questions that you may have. So with that, please allow me to welcome our panel today. Julia Song, co-founder and CTO of ESS. Matt Harper, co-founder and chief commercial officer at Invinity. Russ Weed, founder and president of Cleantech Technologies. And if I didn't introduce myself, I am Vince Sprenkle. I'm the senior advisor for energy storage at PNNL and have been working in the grid storage space for about 13 years now. So with that, I think, Matt, we're going to start off with you. If you want to take the screen, we'll let you go. Matt, I think you're on mute. You may need.
Great, thank you. Yep, perfect. Okay. Thanks, Russ, for the kind introduction and happy to be here with all of you today. I'm Matt Harper with Invinity. Want to walk you through a little bit about who we are, what we do, and hopefully spur some interesting questions and conversation. Invinity is, we're, in our view, one of the global leaders in making vanadium-based flow batteries. We've got the largest fleet of flow batteries that we think has ever been deployed anywhere around the world, with over 275 individual flow battery units currently in service. We have been able to build that fleet by focusing on building a highly standardized, UL-certified, factory-built product. Building out of the factory gives us the ability to build, in our view, at comparatively low cost and high quality. We now have, a fair volume of validated in-field provision of both fast response and long duration services for a variety of customers through a variety of applications on the electric grid. And we are currently in the middle of installing the biggest flow battery projects in the US, Canada, the UK, and Australia. Got about 65 megawatt hours with these products deployed, operate out of operating bases primarily in the US, Canada, and the UK, and have a pretty experienced team who, like myself, have been in the industry and looking at flow batteries and their deployment for a pretty significant chunk of time. How do we view the energy storage landscape? Because this is critical to sort of thinking about the place that flow batteries are going to play. The question that we get all the time is, well, lithium-ion batteries are so dominant. They're being manufactured in such tremendous volumes. How are flow batteries going to have a relative place? And when we think about that landscape, we think about it in two dimensions. We think about the number of cycles per year that a battery is going to be asked to deploy its energy, and then for how many hours at a time in each one of those charge and discharge cycles the battery is going to need to provide power. And lithium-ion batteries have done a phenomenal job of proving at the bottom left-hand side of this graph that there's a great play and a profitable place for energy storage to play on the electric grid. But outside of that narrow area, and especially as we're seeing more and more renewable power being deployed onto the grid, we think that there are much larger opportunities outside of that narrow area, whether that's in applications that require multiple cycles per day therefore hundreds to even thousands of cycles per year, or whether that's in applications where you're looking to deploy energy, not just for an hour or two, but for 6, 10, 12 hours or beyond. Into that landscape, we are currently operating projects in the field that sort of paint out different portions of those capabilities. We have the vast majority of our products in the field are already in revenue service. That performance in revenue service to date has validated a couple of the things that we think are really remarkable about how this battery performs in terms of ultra high throughput, in terms of flexibility, and in terms of durability of the product in the field. That has given us a capability to have deep expertise in not only behind the meter projects where we're saving individual customers money, but also in grid connected projects where we are either bidding into markets for energy, or where our products are serving some of the ancillary services that are currently embodied in energy markets around the world. What you see at the right-hand side of this graph is the performance of our project at the Energy Super Hub Oxford over in the UK over a 1-month period. And this is really validating those two things that are critical to these batteries performing in real time. This battery is doing long duration cycles and trading those cycles into the energy markets, while at the same time, it is responding in about 150 milliseconds to the needs of frequency and voltage regulation at this particular node on the electric grid. So the combination of those two is what drives that ultra high throughput, which in our view is the critical path for next generation storage technologies like ours on the electric grid. Finally, we talked about some of lithium's limitations on the performance side. It's also worth noting that there's an evolving conversation around safety of energy storage systems. Our product has a very, very high degree of inherent safety to it, minimizing costs and risks to personnel, communities, and the environment. What you see along the bottom is some of the projects that we already have operational. These are all over in the UK. On the left, Scottish Water. This is a behind-the-meter solar plus storage plant where we are providing low carbon power at comparatively low cost to an industrial facility 24/7. The one in the middle is a project that is tied to both hydrogen generation and tidal power. And then finally, the one on the right-hand side is the Energy Super Hub Oxford project that we are operating alongside our partners at EDF Renewables, and the data for which you see at the top side of this slide. What does the near-term future look like for us? Where we are, I mentioned earlier, we're building some of the biggest flow batteries in our core markets right now. Just to talk about a couple of those. First off, on the right-hand side here, we're currently in the commissioning stages for what will be, at installation, North America's largest flow battery until the one on the right comes online. But certainly will, for the foreseeable future, be the largest flow battery up here in Canada. This is at Chapice Lake in Alberta, where we are working alongside a solar PV array to deploy energy onto the electric grid. Similarly, in South Australia, with our partners at Yadlamalka Energy, the project in the middle, South Australia, some of you may know, has an electric grid that already has, a vast majority of days where there are negative electricity pricing, similar to what we're starting to see in jurisdictions like California, because of how much solar is being deployed. It's incredibly inexpensive to deploy solar into South Australia, but you need to be able to manage that electricity and deliver it when it's going to be actually more valuable in order to make those plants make economic sense. Finally, on the behind meter side, we're going to be building the largest flow battery in North America, the 10 megawatt hour project that we are building for the Viejas Resort and Casino near San Diego. This is a behind the meter project where we are going to be using our batteries plus a significant amount of PV generation on site to essentially take this whole facility offline when there are critical peak events on the electric grid. Finally, looking even forward out into the future, what I think the sort of the North Star for us is really how are we going to provide net zero baseload? And the tipping point in our view is that net zero baseload will happen when a combination of renewable generation plus long duration storage can be delivered at a lower cost than gas baseload generation. The DOE has a goal of being able to do to get storage, long duration storage at a levelized cost of storage at less than 5 cents per kilowatt hour by 2030. We think we're going to be there by 2026, 4 years ahead of schedule. The reason why that's important is because renewables are already provide very low cost energy, but unless you can deploy that energy on demand, we're not going to be able to use that renewable generated power to fully offset carbon generating sources of electricity. We're working on our next generation product, which we codenamed Mistral, alongside partners at Siemens Gamesa. And with them, in combination with both their wind projects and the solar projects that we're already deploying, we believe, going to be able to do exactly that: take low cost, clean, renewable power and deploy it to make that net zero grid happen as soon as possible. And with that, I will turn it over to any questions.
Yeah, Matt, thank you for that presentation. Hey, I've one quick one I've got is, you mentioned levelized cost of storage and the duration.
Yep.
Do you see that being more adopted by customers looking at that levelized cost, or is it, at first it was all focused on the initial capital cost and people not looking at what's the O&M and everything going into it? Do you see a change in focus?
I do, yeah, absolutely. Similarly to how as the solar industry matured, sort of in the 6 to 10 year ago timeframe, when people started to look at levelized cost of energy or total cost of ownership as a relevant metric rather than the initial capital cost of the product, we do see that shift starting to happen in storage as well. I will say that as you can have the best levelized cost of storage in the world, but if you have to jump through weird financial hoops to get there, or if your initial capital cost is so far different from the incumbent that traditional methods of financing don't make sense, that's really challenging. So I think we are going to have to be in range from a capital cost or a first cost or even an operating cost position. But once those are in range, people will be able to look at that levelized cost characteristic and really understand the benefits of working with a technology like ours. Okay, and we'll do one other question, and then we will save some of your questions. Please feel free to keep adding those. We will have time at the end for a roundtable kind of discussion of the questions also. But a question that came in was, are flow batteries as modular as lithium-ion? Could you start with a smaller system and upgrade it to be bigger over time in a behind-the-meter application? Not all flow batteries are. The company that I co-founded, which was called Avalon Battery, before we merged to form Infinity about 3 years ago. Our founding principles were that we needed to be able to deliver a modular system. If you look at flow batteries that were being built 10 or 15 years ago, they looked like small chemical plants with big tanks and pumps and all that kind of stuff installed on site. And we just knew that we were never going to be able to be a suitable partner for technologies like solar that have a high degree of modularity built into them if we adopted that sort of built-in place approach. So we've really focused on manufacturing something that is 100% turnkey straight out of the factory. We do a full functional test on these batteries before they ever leave our plant. That means that once they arrive at site, they can be installed, wired up, and operational very, very quickly. All right. Thank you, Matt. We'll turn it over to Julia Song from ESS for our next presentation.
Thank you, Vince. And thank you, actually, Matt, for starting the interesting discussion. So my name is Julia Song. I am the co-founder and chief technology officer of ESS, and I'm going to talk to you about also another flow battery technology based on slightly different chemistry. So ESS was founded back in 2011 by Craig Evans and myself. When we started, we like the concept of flow batteries. We like the fact that decouples power to energy, but we're also in searching of a slightly different chemistry that are fundamentally can offer low cost and also sustainability within our mind. So we were investigating iron flow battery technologies back in 2011. And Since then, we had moved outside of the Portland, Oregon, where we are right now. We currently have a facility over 250,000 square foot manufacturing facilities with automation on our power modules. We currently have over 250 employees. And in 2021, we were successfully listed on New York Stock Exchange under the ticker symbol GWH. So you may ask, what's the difference? What is iron flow batteries? So, if you get a energy warehouse from ESS, assuming you peel off the outside of containers, what you see inside essentially half of the containers, here is the tank, and that's where the chemicals are stored. And that's where the energy is stored. And these are the power modules. And these are what the automation line is producing. And that's where the electrochemical reaction takes place. And then we also obviously have power electronics where we boost the low voltage DC bus up to a high, either 800 volt to 1000 volt DC interface, or up to a 480 volt AC interface for the customers. And really the main differences between an iron flow battery, vanadium flow battery, is really come down to the chemistry. Our chemistry is based on starting point is essentially ferrous chloride. And during charge, on the positive side of the battery, ferrous become ferric. And on the negative side of the battery, ferrous actually played out as iron on the plates. So we are not a traditional flow battery, we're really people call hybrid flow batteries. And I would say the key invention that ESS came up with is really come up with the idea how to deal with the side reactions. Oftentimes I tell people, right, if you look at all the electrochemical devices, the main reaction is always simple, straightforward, and it's easy to deal with. And really the challenges come to is how you deal with the side reactions. So we have come up with a very passive and cost-effective design to essentially turn the side reaction back into the solution. That's how we enable the battery cycle to cycle, electrolyte is clean, and cycle to cycle capacity is maintained. That's the technology portion. And if you look at our product, we first deployed our energy warehouse, which are basically the battery in the containers back in 2015. And those are our early, Gen 1 prototypes. We obviously learned a ton. We relaunched our product in Gen 2 in 2020. And these products are 40-foot shipping containers. The interface are 75 kilowatt, nominal power with the capability going up to 90 kilowatt in peak power. The peak energy capacity is 500 kilowatt hour. We made these equipment so that their interface is very straightforward, either AC or DC per customer requirements. And if you follow the news, we've recently received factory labeling on all of our product for UL 9540, all our power modules under UL 1973, as well as the testing pass UL 9540A. The reason we do all these things is to make the product easy to deploy, fast to deploy, easy to commission and permit on site for our customers. Energy warehouse, and if you look at the capacity versus the nominal power, it's really about 5 to 6 hours. So we have another product where it's called the Energy Center. The Energy Center is fundamentally the same technical background as Energy Warehouse, but it's packaged differently. And also, we start to really take advantage of the cheap and inexpensive electrolyte iron flow battery uses. So this system is designed really for 10-hour storage with a power module on the top and the electrolyte on the bottom. These are more for the front of meter solutions, and it's modular design for utility scale deliverable deployments. One of the things we did here's the comparison, sorry, really quick. Here's a comparison of the two products. Again, Energy Warehouse is for C&I customers. Medium range storage. Energy Center is for utility scale customers. It's really for long duration storage. One of the things that I want to cover is that, one thing we did is very early on, we were involved with Munich Re, really try to work with their team, their technical team, and they're involved with our Gen 1 to Gen 2, design changes, lessons learned, how the, manufacturing process improvement that we added in the product, to the point that they are offering our industry-leading investment-grade warranty that we offer to our customer today that not only covers our product, but can also help our customer to cover the project as well. One of the other things I want to comment really quick is, we we are stay very focused with sustainability on our mind, right? We use our electrolyte. The main reactant is ferrous chloride, but we use essentially iron salt as our supporting electrolyte and water. We had participated in independent studies by UC Irvine that shows our global warming potential are about 70% of CO2 emission lower than lithium-ion in the same kilowatt-hour ranges. And we purposefully selected equipment and material that's completely recyclable and easily sourced materials around the globe. In fact, some of our deliverables into Europe and Australia, our customers are excited that they can source a lot of materials locally. So with this as a background, if I get time, I want to quickly talk through a few case studies of flow batteries being deployed in the field and why we're selected. The first one I want to talk about is San Diego Gas Electric. So this is a really first of its kind utility scale deployment for iron flow batteries. In this particular site at Cameron Corner, it's a microgrid. It has the solar. We have total 6 EW systems on site. And the system has a black start capabilities. And the batteries are charged with the solar array during the daytime, but it's really used. The main purpose is to use it to support the critical community infrastructures during what they call a public safety power shutdown events. And however, because the customer has the assets, when they are not delivering any backup power during the PSPS events, these systems are capable to use daily renewable energy shifting. They can be used for load management. They can participate in the CAISO markets. And the reason we won, one of the most important one is safety. Because this Cameron Corner site is in a wildfire zone. So, they are looking for battery technology that has no risk of thermal runaways. And in addition to that, we also offer the ability to provide additional services to our customers. The second one I want to talk about, this is an announcement we made last summer at Intersolar that we are working as a partnership in a multi-year agreement with SMUD that ESS will supply up to 200 megawatt and 2 gigawatt hour of iron flow batteries, including energy warehouse at the beginning and the energy center later on. And it starts in 2023. And our team is working, we're on schedule to deliver the product. And what's getting me really excited about this project is that we're not just focused on delivering or deployment of iron flow batteries. We're also working with SMUD to essentially set up facilities for battery system assemblies, for local support training with the local educational institutions to train local workforce to support O&M and to essentially build up a really sustainable workforce to support the growth of long duration energy storage in California. So these are two examples I have essentially for utility scale deployments. The next two I want to talk about are use cases that's really more C&I use case. So in Q1 of 2023, we've deployed our system to Amsterdam Airport Schiphol. Schiphol is actually second largest airport on the mainland Europe. And the reason they are trying to test out the idea is essentially using the ESS iron flow batteries to connect it with solar, get charged, and use the power stored in the energy storage system to really replace the mobile diesel grunt electrical generators that's currently used today. And this obviously was an early stage demonstration project, but the goal with the Royal Schiphol Group, it's really that they have set an ambitious plan for all of their airports to be emission-free and waste-free by 2030. So we see this as a major growth potential for us. And the reason we got selected, it goes back to the sustainability page where we show a very low, CO2 generation of our product compared to lithium-ion. And in addition to that, it's by the airport, so safety is definitely on their mind. So between the safety and sustainability is where ESS technology got selected. The last but not the least, I want to talk about TerraSol. TerraSol, this is a project that we're working with TerraSol Energies. This particular project was deployed last year and commissioned last year. It's running on site at Sycamore in Pennsylvania. It's connected with 115 kilowatt DC solar panel on site. And what's unique with this one is that the system is really used for multiple use cases. We're used not only for the, for supporting daily, solar shifting, but also we're supporting peak demand as well as peak shaving for the customers. In addition to all of that, our system is also used as a backup power. In fact, just last week, Sycamore had a shutdown event locally where the customer essentially didn't even experience, they didn't even realize it happened because the ESS battery essentially supported the building without even a light blink. So, I hope that this range of different examples kind of show you, where flow batteries and really what the market is going on, why more and more people are selecting flow battery technologies and for their applications, really thinking outside of lithium ion. Because flow batteries, we're designed to run cycles. We have the chemicals outside the battery module that gives us the opportunity to essentially balancing the electrolytes so we're durable. We're also very cost effective, especially if you consider not just the upfront cost, but also the total cost of ownership of a project. And I would say that more and more customers are becoming more aware of the overall cost of owning these, long duration systems. We're easy to site and deploy, and the safety is definitely becoming more and more important in the customer's mind. So with that, I ended with a video, but obviously I'm not going to play that. But if you get a minute, if you go on YouTube and searching ESS factory tour, this was recently posted, would really give you an opportunity to go through essentially inside of ESS and see how we build our battery, how we integrate our full systems. And at the very beginning, Eric also going to walk you through essentially our development path from early days, 50 square centimeter cells to where we're making today as 100 cell, over 3,000 square centimeter of size of flow batteries. So with that, I think I am probably way over time, but yes, thank you.
Yeah. So we did have a few questions. We'll try to get to a couple here, and then we may get to a couple later.
Sure.
One asking, are there any rare earth elements in the flow battery, or is it
Not in iron flow batteries.
an iron? So okay. And then there was a question on, we especially with flow batteries, we tend to look at large scale systems, utility tied, in general, not just yours, but do you see applications for smaller scale systems in there?
I think it all comes down to the economics.
Okay.
Right, because the flow battery does use it's different. Sometimes, I thought it was funny. Matt mentioned that it's like a chemical plant. It's really, if you think about it, it's just not a traditional battery. It requires others, it requires the pumps, it requires the chemicals. There's benefits come with that by decouple things, but there are also things come with it where you can absolutely do it, but can you do it economically? And that's going to be the challenge.
All right, thank you.
Sure.
All right, and I encourage you to keep putting questions in the chat. We'll have time here after our last speaker. So without further ado, Russ, are you ready to go?
Yes. I need to be given permission. I think you need to pull yours down, Julia. Thank you. Okay, Russ Weed of Clean Tech Strategies. This is going to be a fairly different presentation from the two that you just saw, which are solution focused, one vanadium flow battery, another an iron flow battery, but you will see that that is interwoven in here. What I want to do here is take a step back and think about the innovations that have happened in the flow battery industry during the time that I've been involved with it, which is since 2012, so about a decade now. And I will swear to you that neither Matt nor Julia saw my presentation, nor mine, nor I theirs before this. So it's going to be pretty interesting coincidence, some of the things that I'm going to address here. to mention, this is does not purport to be a exhaustive discussion of the diffusion of innovations in the flow battery industry. This is the first presentation along these lines that I've given, and so I'm going to call this version 1.0, and there shall be more built out ones to come. When you get a copy of this, if you get a copy of this, you can see the 5 of us at Clean Tech Strategies, 3 double E's, 2 of which are PEs, 2 JDs with a great deal of experience in the energy storage industry. So there's the 5 of us. Now, the topic of my talk. There is a great book called The Diffusion of Innovations. If you have not seen and looked at this book, see if I do the depth of field correct here. I highly recommend this book, though it is about 500 pages long. The first edition of The Diffusion of Innovations by Everett Rogers came out in 1962. And I think pretty remarkably, Professor Rogers maintained this book through 5 editions for 41 years up until the 5th edition here. Another thing that's quite interesting to mention about Rogers is that he's a sociologist. He's not a technologist. So we're going to use a basic framework that Rogers came up with for discussing how flow batteries have innovated to become better. And I think you've just seen a couple examples of that. If you ever wondered, as I did, which is the reason why I found the book, where the term early adopter came from, it came from that book, from Rogers. So, and as you can see in this, this copy from the book, and you're going to see a few of these, because I thought that having seen this curve and how instructive it is, that there had to be other charts in that book, and indeed there are. I'm going to show a number of those. So this shows the progression over time, from left to right, of adoption of technology. And that book is filled with all different examples. So energy storage, which of course I love, is just another example. You start with the innovators, then you get to the early adopters. We know that term in particular, maybe the one that hasn't, 2 that haven't been used as much: early majority, late majority, and laggards. If you have seen this way of thinking, this framework before, and wondered why it was such a perfect bell curve, when you read the book, you'll see it's because that Rogers is also a statistician. So this curve is based on the top of the curve being the mean, and then the vertical lines that sectionalize things into the different groups. Those are 1 standard deviation and then 2 standard deviation. In reality, so this, I call this statistically idealized. In reality, of course, the curves are not symmetrical, and in fact, they are going to have the peak later in time. And this is an example of that from the book. And I genericize the different examples, but if you want, pretty good analogies to what the particular thing you're looking at, you will find them in there because there are so many. To me, this really is an important chart because it has here 3 innovations, and it has some language there. I think pretty simple way of thinking about it. So what does it take to diffuse innovation? So you need the innovation. You need to communicate it through channels. I think that's a very good term, channels. It's used very much in the commercial world, for example, channel marketing, et cetera. You need time, and you need a social system. Remember, of course, that Rogers is a sociologist. So this shows 3 different innovations, genericized, and you can have different curves. And I regard what we're doing here today as hopefully increasing the slope of the curve to encourage further adoption. Because I think there are capabilities of the flow batteries that you just heard briefly mentioned that you might not have known before. For example, the ability to do power functions as well as energy functions or applications. Now, to that point of what we're doing here as a group, one of the things that is studied is that particularly in the early stages of adoption of a technology, of an innovation, a lot of the adoption is due to interpersonal communication. In other words, what we're doing right here. So when looks further at that, makes common sense that depending upon what category you're talking about, are you talking about the innovators, the early adopters, the early or late majority, or the laggards? There tends to be more or less reliance on the interpersonal. And this chart shows moving through 3 stages of adoption. One is getting to know about the innovation. Second is to get persuaded about it. And then third is to make a decision to try it. This, of course, is one case. I wouldn't claim that this would be empirical in all cases, but an interesting point that for the innovators, it's not necessarily an interpersonal thing. It's because they're inventing, right? Whereas as you move up the adoption or down further on the adoption curve, the importance of the interpersonal increases. Apparently, laggards need to hear that something is good and useful and cost-effective from a good number of sources before they'll proceed. And so here, another chart from the book shows what actually happens in reality in terms of the diffusion of innovations. It's a spaghetti. This organization, this person is communicating with this and exchanging this information and so forth. So this is a framework for thinking about how flow batteries have gotten better, how they've innovated the last decade. And again, Matt did not see this presentation. So, and a very important flow battery innovation is to go from having chemical plants, and here is an example, Enervault, not to be confused with Energy Vault, a more recent company. Enervault, iron chrome flow battery. This is a picture from approximately 2014. And it's 250 kilowatt, 1 megawatt hour. A particular specific thing about iron flow batteries is a single pass technology. Therefore, you need a tank at the end of the flow of the analyte. And so you need 2 tanks per analyte and catholyte. Thus, I think it is fair to say that this looks like a chemical plant. And then, and I did pick, the examples I picked here were of ESS and Infinity, which I thought was the right thing to do. But there are, of course, other examples. This is an industry trend of adopting certain innovations that make flow batteries better. So a really important step that the flow battery industry took was to containerize. And here you have, as Julia described, their energy warehouse product. It makes a great deal of difference to the customer that the product can be delivered to their site in a box. And then the flow battery industry, again, giving Infinity as an example here, there are others, to modularize. So to go to that question that was in the chat, to modularize is not the same thing as containerize, of course. You can, as you can see here, Matt didn't mention it, but you can, what Infinity has done is taken 6 modules and packed them together for their current product, though, as mentioned, there's another product coming. Why is modular important? One reason was addressed in the chat, which is to make the system extensible. But there are a number of other reasons as well. One of which, given my experience in flow batteries, a very important one is that you not have too many kilowatt hours subject to points of failure. Now you have to go through failure analysis, right, for a piece of industrial equipment. So to bring it up does not mean to wish it to happen or want to see it, but one must plan for it. And modular it enables a significant amount of risk reduction in terms of single points of failure. So that's something I would look for those who are on the line here on the webinar here from utilities, for example. Has that flow battery solution taken the modular step? Because not only for single points of failure, there's a whole other number of things that can flow, so to speak, from that approach. So I just listed them out here, not seeking to go into them exhaustively as mentioned. But one reason to go modular or concurrent with it is to have, relatively speaking, smaller stacks. It has been done in the flow battery industry to have very large stacks, like 100 kilowatt stacks or 50 kilowatt stacks. I am not an electrochemist, but I have heard the term shunt current enough times and heard enough times how unwelcome they are in flow batteries. Sorry for the simplistic way of putting it, basically lightning through liquid. You want to mitigate shunt currents. That's a very important thing in managing a flow battery, including for the reasons it ties to what Julia was talking about, managing or eliminating side reactions. The shunt currents are unhelpful in that regard. Also, by having smaller stacks, and the reason that mitigates shunt currents is because by having the smaller stacks, you keep it at a lower voltage, and that mitigates shunt currents, and also hot spots inside of the stacks. Hot spots, both in the sense of temperature and pressure. You can manage the flow inside of a flow battery stack much more when it's at a smaller size compared to some others that were previously the approach. Another, stacks above the tanks. I had looked more before this presentation at the energy warehouse product for ESS. I noticed, and Julia showed the energy center, the stacks are above the tanks. It's very useful to have the help of gravity to evacuate the electrolyte from the stacks if the system is going to be sitting idle and you are not needing a warm start. In other words, keeping the electrolyte in the stacks. If the system is going to be idle, it's very helpful for the health of the system to have it, the electrolyte drain and put the stacks above the tanks. As mentioned, keep the voltage of the stacks lower. Then that means that you have to use more DC-DC power electronics. And this is going to be an area of improvement. And in fact, I'm at a conference here in Alaska. This is an opportunity for the US in terms of made in the US power electronics. Flow batteries are going to take a lot of the medium duration, I call it, market that Matt addressed in particular, that 4 to 10 hours discharge duration. And with that occurring, we're going to need a lot of DC-DC power electronics for flow batteries. So hopefully that's a market that we can further develop. There are a couple of manufacturers, US-based manufacturers of that now. Was not the case 10 years ago. Maybe a time for a story another time about their unavailability 10 years ago. And then also another innovation that has taken hold. It depends on the chemistry, of course, but additives to the electrolyte have become a very useful innovation. For example, with the vanadium flow battery, if one wants to increase, let's say, the molarity of the active species, one could do that by using 2 acids, or as it turns out, probably better to use an additive. So those are a couple or several things that one should look for, I think, in saying how far evolved in the innovation that a flow battery system is.
Hey, Russ, we need to get moving to Q&A.
Okay, so if you're interested in these things, come join the Flow Battery Industry Group. We've established it under the auspices of BCI, Battery Council International. We have some founding members. Please be in contact to participate in the Flow Battery Industry Group, which is active on a number of these things that I've mentioned. Thank you.
Thanks, Russ. So we've got quite a bit of questions coming in. I think I'll go ahead and have Julia and Matt join us if we can, but I'll let you lead off the first question here, Russ. So there's questions again about the flow batteries needing regular maintenance during their service life. You know, do you kind of in general terms, what do we look at in terms of that? Or if you want to defer to anyone else, we can do that.
I can address it generally. There's a maintenance schedule as there is for any piece of industrial equipment. It's scheduled. If the system is properly engineered and manufactured, it should be less maintenance than a lithium-ion battery. Lithium-ion batteries degrade, you have to augment, and so forth. So sure, prove it, but the O&M on the flow battery should be less expensive than on lithium.
I agree, Russ.
Yeah, and look, the only other thing that I would add to that, picking off in part the question about longevity and lifetime, you know, really it comes down to a repair or replace decision at the end of life. You know, we're looking at a 25-year life for our products in the field right now. Could we extend that to 26 years by continuing to replace components? Absolutely. Are there likely to be, you know, new innovations, to your point, Russ, that we want to embody and therefore install a whole new product by the time, you know, a fully amortized asset is 25 years old? Quite conceivably.
All right. Thank you. So we did get a couple questions. You know, one of, I would say, I guess a misconception of flow batteries is they are energy and not a power system. And so the question was, you know, how fast can these systems respond to it? And then, yeah, how does that compare to like what we're able to do with lithium ion?
I'm happy to start. So we validated response times of about 150 milliseconds for our batteries in the field. That's limited primarily by the response time of the control system and power electronics, not by the electrochemistry of the battery itself. I would note that overperforms or outperforms a lot of lithium systems. And certainly it's within the limitations that are set for most of the jurisdictions that we operate in, where we're looking at provision of ancillary services and the performance requirements for those kinds of applications.
You know, I completely agree. I think that's a total misconception, right? Even if for me, it's like a battery is a battery, right? If you just look at the pure electrochemical device, it is an electrochemical device. There's no reason fundamentally at all that flow battery somehow cannot support grid support functions. In fact, that I think because the flow batteries, you know, I don't know, in the Infinity system, in our system, we actually, in that container, we provide the power electronics that boosts up the voltage up to, you know, the proper voltage to support the load, which is exactly why our customer at TerraSol basically said that they didn't even know they lost power. The system transition essentially so seamlessly, they didn't even see the light blinker. They only later on, when they look at the data in their, you know, in their HMI, they realized they had lost power for a period of time. I think so flow batteries, in fact, some of our application with SDGE and SMUD specifically required grid supporting functionalities.
Here's the layperson point. Just because the electric flow between charge and discharge goes different directions does not mean the mechanical flow of the liquid does. I've heard, you know, I thought that 10 years ago. I've heard engineers recently wonder that. So the flow path does not change mechanically when charging it. So that would be a logical reason for response time being slow, but it's not correct.
All right. Thank you for that. And I apologize to everyone online. We're not going to have a chance to get to all of the questions here, but I appreciate all of your input in here. I think I'll kind of some of the ones that are looking at the big challenges. So what do you see as the main challenges for scaling up to gigawatt scale for flow batteries? You know, is it supply chain? Is it other barriers that you see that need to be addressed to get up there, or is that on the current path? So, Julia, do you want to start?
Sure,
Sure.
yeah.
Matt, go ahead.
Yeah, okay, sure. Look, I would say it's everything. I mean, gigawatts of capacity is, you're talking about hundreds of millions to billions of dollars worth of product flowing through factories, going to customers, all that kind of good stuff. I mean, the logistical challenges of getting something like that built up are pretty significant. We're fortunate in that we, like you do, Julia, work with an active material that's pretty widely available. We get vanadium from all over the world, so we can work with that fairly easily. And then the other aspect is, one of the things we usually talk about is that we don't need to build a gigafactory to build one of these products. We can put flow batteries together comparatively easily, close to the point that they're eventually going to be used. So that flexibility in the supply chain is part of what we're going to use to get over some of those challenges. But it is building that industrial scale is a heavy lift.
I would agree to that. My own personal experience, basically going through the journey of ESS from a R&D kind of stage to where we are. I think I certainly myself start to appreciate a lot more on the challenges of supply chain, right? And the challenges, and especially with COVID right in the middle of it, just how some area like disruption during COVID time can affect our entire, production lines for this one material that we're missing, which really hammered to the point of why we want to focus on using earth abundant, easily sourced materials that you can really get anywhere around the world to minimize that risk.
The main obstacle is adoption, and we need knowledge, persuasion, and decision.
Okay. So I'm trying to wrap up a few questions here into a single one, but I think we're all aware that we've seen a more emphasis on the end of life considerations of these storage as it's growing. It wasn't always talked about, but I think we all have a hard time, not talking about it now. So, there's a question about, are these recyclable? What do we do at the end of life? And then I think, Matt, to you, there was a question on that whole value chain of vanadium, the resource where it's coming from and how you do that. So.
Sure. Okay, well, let me address those two separately. First of all, on the recyclability side, the vanadium electrolyte we use is infinitely reusable. We've reused electrolyte in multiple successive projects because the vanadium in the electrolyte itself doesn't change over the life of the battery. Other than the vanadium electrolyte, the balance of the system, we've calculated it's about 99.9% recyclable, and not recyclable using esoteric, industrial processes. These are materials like polyethylene, polypropylene, steel, aluminum that you could literally put into your, municipal curbside recycling system if you wanted to. On the supply side, vanadium is one of the most common elements in the Earth's crust, not as common as iron, I will admit, but it's it's the 13th most common metallic element. It's more common than copper, more common than nickel. The stuff is literally available anywhere, and so we have sources of supply that we use here in North America, in Europe, in Asia, in South America, in Africa. That it's very, very widely available. The question for us is always, where can we get the most reliable source of supply? And also, how can we minimize the the transportation and logistics around getting that to the factories where we blend that material into the electrolyte?
Yeah, no, absolutely. In our case, we are still using recycled electrolyte from 2015, 2014 timeframe. And in some of the cases, when our customer, for example, they don't want to ship the electrolyte back to us, they could easily, like we use iron, salt, and water. The way to dispose it is as simple as raise the pH and everything will precipitate, filter it out, and that's as simple as it to recycle or reuse or dispose of the electrolyte. We purposefully, selected materials that are all recyclable in our system. So you're absolutely right. I think a lot of time people really didn't even think about the end of life. What do we do with these batteries, right? The early, 10 years ago, when a lot of lithium-ion put on the market, but now we actually have customers come to us because they have these lithium battery, they don't know what to do with them. And all of a sudden it became a problem they have to deal with, and they want to start considering, hey, the full life cycle of this product, not just the beginning cost or the beginning installation of the product.
So the pro forma for your projects must have a line for cost of disposal or recycling. It used to be that the spreadsheets didn't have a line or rows for degradation of the lithium cells. Now they do. We also need to have lines in those spreadsheets that cover the cost of disposal or recycling. That will have a major impact on the LCOS.
Thank you for that. And Russ, I just saw one come in. Can you repeat the name of the industry group?
Flow Battery Industry Group.
Okay.
Flow Battery Industry Group, which happens to work out in terms of an acronym to FBIG.
Thank you. So we've got a couple minutes. I wanted to open it up to each of you if you've got a closing comment. I really appreciate your insights. We had a lot of engagement, and I apologize to our audience that we couldn't get to every question that was out there, but you all did an excellent job kind of outlining where flow batteries are today. So we'll start, Russ, I'll start with you. Do you have any closing comments?
Yeah, I'll answer one of the questions that was in there. The main, a very important application of medium duration storage, 4 to 10 or 12 hours discharge, is shifting, energy shifting, matching up to renewables. It is, in my opinion, the most important area of energy storage right now, which is not to take away from short duration storage, not to take away from long duration storage, 10 to 100 hours, not to take away from seasonal, but the thing we need the most right now is medium duration, 4 to 10 or 12 hours discharge, so that we can get more renewables online more quickly, so that we can make that curve happen faster.
Julia, Matt, either one of you want to have any parting thoughts or?
Sure. I just want to remind everybody, there is another misconception that somehow flow battery is not ready or is not mature. And I don't think that's true. I think Matt's shown it, ESS has shown it. We are ready. And I think it's really a mindset change of the people, right? Of the customers. Goes back to what Russ presented, is that think about the total cost of the ownership of the project.
Julia, couldn't agree more. I guess if I could add one final thought, it would be to reinforce a theme, or to tie together a theme that's come up in a couple of the conversations here. We can go and develop all the best technologies in the world, but it is the mutual sort of understanding of how these technologies operate, the innovations that stand behind them, and the opportunities for the market where they make a lot of sense, that are really going to drive this to the multi-gigawatt hour opportunity that we're all focused on. A big part of that is, not just the diffusion of innovations, but the diffusion of understanding and knowledge, and that starts with events like this. So thank you, Vince, for the opportunity, and thank you all for being part of it today.
Yeah, thank you all very much. I think you did a lot to demystify the world of flow batteries, and I appreciate you doing that for our audience here. Thank you all for attending, and we look forward to having you at our next webinar, which I think is coming up on a slide. All right. Sorry, I'm having issues. I don't know if you can still hear me or not.
Yes, we can. Thanks to PNNL for the webinar series.
Yeah, thank you.
I don't know that you mentioned this, Vince, but there's like 12 or 15 of them that have already occurred that you can pull up on the website, and it's a smorgasbord of topics there.
Okay. Thank you all. I'm glad it waited till the very end before it kicked me out. But I'm back. So yeah, thank you. If you go to the PNNL grid storage, you can see the previous examples and recordings of it. We'll have a recording of this episode too, but on Thursday, June 1st, we're looking at transitioning of the electric fleets. That's looking again kind of with some of the work that we're doing here in the Northwest with Tacoma Power, Franklin Pierce Schools, and King County Metro. That'll be led by Christine Holland at PNNL. And then we're looking at it on July 20th, energy storage for grid resilience. And so Diane Baldwin at PNNL will be leading that panel discussion. Once again, thank you all for your time. Really appreciate having everyone join today. And again, a big thanks to our panelists today. Thank you.
Thank you.